your matter is not CP symmetric. You don't have positron. If you would have been having positron there, then nu E bar and positron will fill the same diagram, and they will feel the same potential, same probability. You will get the difference to be 0. It is just like matter. In matter you have electron, but you don't have positron. So nu E bar is not getting that fellow with whom it can have the elastic forward, coherent elastic forward scattering.
But then, sir, nu E bar can annihilate, but the probability is very small, so it effectively won't. I mean, it can through a Z, right?
Z, yeah, but you see, in matter, they are not. It's like, you know, there may be some contact interaction of neutrino or anti-neutrino, but you are talking about billion neutrinos. Out of that, if 1 or 2, like you can understand when this interaction is happening, this nu E can convert into E also, right? Because nu E going to nu E, right? But that interaction, that cross section is too tiny. So when nu E is coming, passing through Earth, it can have a hard scattering, as Eddie was telling. If it has very high energy, it will have hard scattering, and nu E will not remain nu E. It will just be lost because it will go to electron with hard scattering. But when your energy is very low compared to the mediator mass, okay, then you can have this, you know, this is potential, this which can be added up, because neutrino has to be neutrino. It can't go to your charge partner. Okay, did I answer your question?
So one more question. In such cases where the neutrino will interact with an electron, I mean, you can get in the final state of muon and a muon neutrino, or an electron and a muon neutrino through mixing. So, I mean, those things should make the calculation more difficult. I mean, on top of this matter effect.
Yes.
It's not always guaranteed that if an electron and a neutrino will, but then there is like lepton number violation sort of. But
yes. So people have done that. Even I have written also a paper where you don't impose that condition, and then you know you have different kind of diagrams. Finally, you want to see. Suppose your detector is sensitive to electron. You want to see how many forward scattered electrons are reaching in your detector. But that can happen. But if you just don't impose that lepton flavor conservation or lepton number conservation, you will have different diagrams that you need to take into account, and it will give you different potentials in the mass matrix. Your probability will be different, and your experiment should see them. Very good question, and this is a hot topic now. Even our supervisor worked 15 years back, but still this is a very hot topic, because now the data is precise. Any departure from your standard scenario, your data can be able to probe that. So they gave those ideas, but now this is the time where you can validate their ideas. So you have asked a very good question, and it's an industry now. So good thing about that, you have this potential, but this is positive for neutrino, negative for anti-neutrinos. This is just due to the SU2 structure of the standard model. Okay? Because there is a nu E, it is coming, and you also have a nu E bar, your question, but in matter you have only electrons, so your potentials are different. And when you need to take into account that potential, I will show when you will diagonalize in presence of matter this mass matrix, your probability will be different. And if you can measure the probability separately, you can also confirm that okay, this is for neutrino, this is for anti-neutrino, but there will be another information. So take home message, there is no positron, that's why there is a difference. Otherwise,
usually which probability is large, for neutrinos or antineutrinos?
good question. So if you are just talking about probability, there is another guy which comes into the picture, is the sign of delta M square. If you know the sign which is not known, and if you know neutrino, so if you are looking for say nu E to nu mu probability, and if you have neutrino, and if the hierarchy is normal, like M3 is higher than M1, that probability will dominate. But if it is inverted, then nu E bar going to nu mu bar, that will dominate. And immediately you will see how. So potential, so there is a nice potential is cropping up in your picture, and they are different for neutrino and antineutrino. This is clear, right? Because in atmosphere you have neutrino, antineutrino. In your beam you can have a neutrino beam or antineutrino beam. When they will face the matter, for neutrino this is the plus sign, this is the minus sign. And how you connect? So it is proportional to the density of the electron, and this is a nice expression. You just plug the density of the matter and the energy, and you can calculate this term in this way. You just need to know what is the density of the matter, how much gram per cc. You just plug in there, and you know the energy in GeV of the neutrino, and you know the potential. Okay. Now matter term changes sign from neutrino mode to antineutrino mode. I just explained. Remember again, you have only electron, but you have both nu e and nu e bar. You don't have positron. Otherwise, they would have cancelled. Okay. So, but then if you are sending a neutrino beam, antineutrino beam, taking their difference, this can be non-zero, as I told you, because that fellow is now entering into the probability. So even if your Cp phase is 0, because what is the difference? Why you need Cp? Because you need both charge conjugation and parity to go from neutrino to antineutrino. And you would become U star due to the presence of delta. So you expect, if there is no matter, and if you see that difference, then definitely that difference attributes to that delta Cp phase. But now if you are doing your experiment and you are unlucky because there is matter, you are lucky for some other cases, then there can be difference in the probability just because your matter is not Cp symmetric. You have only electron, you don't have positron. So matter will also cause a departure or a difference between neutrino and antineutrino probability. Is that clear? You have a neutrino, you have an antineutrino beam, you are measuring their probability because you are seeing their number of events which are different. Your goal is to measure that phase. All the angles have been measured. But unfortunately, neutrinos are traveling through matter. So what you do, you just see the difference between n and n bar, the number of events. But that difference can come from two ways. One is due to this delta phase, because when you will write this probability for antineutrino, I wrote U becomes U star, delta Cp becomes delta Cp minus delta Cp. That is the only difference as far as oscillation is concerned. So if there would have been no matter, you just see the neutrino probability, antineutrino probability, take the difference, that is due to that Cp phase. But now you can't do that. You do that, but then that difference can be non-zero even if that phase is 0 due to matter effect. So the game in neutrino oscillation physics is now our topmost priority, which we think every day, how we can disentangle these two effects. One is the genuine Cp phase effect, another is the dynamical Cp phase effect due to matter effect.
But isn't this matter effect can be calculated precisely?
Yes, but it has always error. You don't know the density very well.
Because you know the length.
Yes, but there is an error because you see this phase, measuring the phase is not easy. That's why we are waiting. It's the hardest job. So it is like the difference is of the order of 5%, 4%. And if I take 2,000 kilometer distance, and if I want to tell me what is the average density, always I have 2% error in that. The Earth model that we have is not that precise that you can just nullify this, you can subtract this effect. Okay, so that is the game. When you have a data where you probe neutrino probability, antineutrino probability, that means neutrino event, antineutrino event, you want to fit that delta, there is a matter effect is coming, which is your obstacle. How to filter out? This is the modern neutrino oscillation experiment question. Okay, how to filter that effect? Okay, this is what we do in IOP. Our group is involved to just ask this question, how we can separate these two things. Okay, so matter term modifies oscillation probability depending on the sign of delta m square. as I was telling you, there is another caveat that you need to take in mind. When you are calculating the probability, you need to know which guy is going, neutrino or antineutrino, but the probability will also be dependent on whether the hierarchy is normal. So here hierarchy means I am asking this question. DP told that there are 3 flavors, there are 3 mass eigenstates. From solar neutrino experiment, he explained that M2 is heavier than M1. But the data that we have now, it allows both this picture. This M3 can be here because we know the splitting, the magnitude of the difference. But whether this delta M square atmosphere, this fellow, is positive or this is negative, because we know the splitting and we know that M2 is heavier than M1. So this issue will, along with your matter effect potential, will give you a certain probability. So you see, matter is an obstacle for CP measurement, but matter is a boon for your hierarchy measurement. Okay? If there is matter, there is a matter effect, then it couples with this hierarchy sign in the probability, which I will explain now. So then you can also tell what is the sign of this quantity. So in some cases, so this is a unit of electron volt square, right? You can calculate an example, take an example of Earth. Suppose if you take CERN to IONO distance, where Arun works, where I work in IONO. Okay, take this distance, it is 7,000 kilometers. That was my thesis work, 7,200 kilometers. And this is a magic distance, which I will not be able to explain now. But this distance, if you take the line average constant density of that CERN to IONO, so this is your Earth, this is your CERN, somewhere this is your IONO. So that distance is, so you are passing through lower mantle. And say I have an Earth model with 3 onion layers. So that density is ρ1, that density is say ρ2. So basically your average density is ρ1 and this distance is L1 plus ρ2, L2 by total L, right? This is the line average constant density of the Earth. And if you take the Earth model for this 7,000 kilometer, this rho is 4.2 gram per cc. Okay? So you know this. Now, you know that, so that you can calculate this. And your energy, say, if I shoot a beam of neutrino from CERN, so of say 5 GeV, you can calculate this quantity. You need the energy, you need the rho, I told you. You calculate this. And you will see that value for 6 to 8 GeV neutrino beam will be exactly similar to the value of this delta M square, which I just showed. This splitting, which is 2.4 10 to the power minus 3 electron volt square. This is the best fit of this splitting. So this quantity delta M square atmosphere, it is in electron volt square unit. That matches with this potential which I just calculated for CERN to IONO baseline. And if these are same, so you see that there can be a case, if you do this experiment, your matter potential, the magnitude, can be similar to this quantity. Okay? So you are comparing this. Now you will see the MSW enhancement. MSW means your θ13 is 9 degree. This is the bare value. You know that all the parameters run, right? You measure Weinberg angle at 90 GeV. Now if you just extrapolate that running, this is the Weinberg angle running, you can measure, and he is an expert of running of everything. So if you can measure at 90 eV, you know what is the value. Like all this mixing and mass parameters, I told you these 6 parameters, when you send these neutrinos are traversing through matter, they also run, but run as a function of this matter effect. So you start with a theta 13 9 degree, because this is the measured bare value. But in matter, theta 13 can become the highest mixing angle, which is 45. So this mixing angle gets enhanced in matter. So that means it is running not as a function of energy in case of other parameters, but here it runs as a function of matter effect. Okay, and it can attain the highest possible value, which is 45 degree. This is called the earth-matter resonance. Okay, but that resonance will happen if you have a neutrino and this fellow is positive, because you know for neutrino this potential is positive, and if this delta atmospheric is also positive, that means if it is normal, then only that enhancement will happen and you will see a huge nu mu to nu e or nu e to nu mu conversion, 50 like 0.5, 50% conversion. That will happen for anti-neutrino if this delta m square is negative. So the take-home message, if you have a neutrino beam, if you have an anti-neutrino beam, this fellow is well calculated within 5% error. You know the density of the earth. The calculation you can do, you can get this value A. But now you look at the probability. If theta 13 is 9 degree, the nu e to nu mu conversion rate is 10% at most. But if there is a nu e and this delta m square atmospheric is positive, in matter this probability can go to 50%. This will happen for neutrino if hierarchy is normal. This will happen for anti-neutrino if hierarchy is inverted. So your job is observe both of them, sit back, count, game is over. Now at what confidence level you want this game to be over, that is your personal choice. And this is the main philosophy of INO experiment. INO will observe atmospheric neutrinos, both neutrino and anti-neutrino, and these neutrinos will mainly coming from the earth, and earth distance is, you have 7,000, you have 6,000, you have 5,000, 4,000, so this situation can occur.
So what are the other experiments for mass gravity sensitivity?
Dune experiment from Fermilab to Homestead, their baseline is only 1300 kilometer, but still they are sensitive. Their theta 13 will not reach to 45 degree, it will reach to say 22 degree. But there is a matter enhancement, same game. Okay, so matter can be your boon, can be your tough life. Matter is tough for CP measurement, matter is great for your hierarchy measurement. But this is life, there is always matter. Okay, except reactor experiment where you have the distance 1 kilometer. But if you go just 100 kilometer, your earth density is already 2 gram per cc, just for 100 kilometer. Okay, so I have a picture for you. This is the earth radius I plotted in my thesis, taking that model, what is the line average density. So you can see this line, this upper plot, this is the line average density of earth as a function of L. And you can see here, if it is 7,000, the value is around 4.2. But when you are passing through core 10,000, 11,000, there is a kink in the matter profile, because all of a sudden the density jumps from 4 to 10. But since I am doing this averaging, but still you can see a kink there. So this is the kink, where you pass into core now. Okay, neutrino trajectory passes core. And this resonance, I just calculated that what energy of neutrino you need to have resonance means theta 13 will become 45 degree. This is the function. So this is the expression. The resonance energy can be written like that if you just neglect the solar frequency, because here you are working in GeV range, your baseline is so high, so you can drop this delta m to 1 square. Okay, and this is the expression. So